So today my plan is to talk about this dimensional rigidity and the universal rigidity. So I'll talk about some stuff that about the characterization of the universal rigidity with connection to the stress matrix. And there's a nice theorem from Connelly, which I will prove. So this theorem I want to prove in the end. So this is the main theorem. I want to prove. Okay, and so we said we have a characterization of the universal rigidity in terms of the PSD matrix, PSD stress matrix. Okay, so this is basically from the Abdul's book, chapter 10. Yeah, chapter 10 of the Abdul's book. So let's first look at the definition. So what is a universally rigid framework? So given let GP be an R-dimensional bar framework with n nodes, then GP is said to be universally rigid if for any integer s, s in any s between 1 and n-1, there does not exist an s-dimensional bar framework such that each Hadamard product dp and dp is not equal to dp prime. So this H is just the matrix called the adjacency matrix of the graph G. So H is the adjacency matrix of the graph G, and this one is the Hadamard product. So in other words, GP is a universally rigid if every bar framework GP prime that's equivalent to GP is actually congruent to it. So there's no dimensional requirement. So it means that in any dimension. So for any framework in any dimension, if the framework if another bar framework is equivalent to GP, then it must be congruent to it. So universally rigid just means that it's a global rigid in any dimension, right? Think about the global dimension. So if a framework is globally rigid in dimension R, but it can be non-rigid if you go higher dimension. So universal rigid said that this is impossible. So you cannot lift it to any higher dimension, and you cannot lift actually find a lower. You cannot go to higher dimension, and you cannot go to a lower dimension. So this is the definition of the universally rigid. Now here's a definition of the dimensional rigid. So the definition is that given an R-dimensional bar framework with n nodes, then this framework is said to be dimensional rigid if for any integer s, s is between s plus 1 and n minus 1, and there does not exist an s-dimensional bar framework GP prime such that each Hadamard product dp prime is equal to each Hadamard product dp, and also dp is equal to dp prime. I forgot this. So in other words, if an R-dimensional framework bar framework is dimensional rigid, And if GP prime is equivalent to GP, then GP is of dimensional R or less. Okay, that means if the framework is if R-dimensional bar framework is dimensional rigid, then you cannot go up. You can only go go to a lower dimension, but you cannot go to a lifted to higher dimension. So it's obvious that universally rigid implies dimensional rigidity, but not the other way. The other way is not correct. So to characterize this universal rigidity, we have, yes.
Can you give an example of the that dimensional rigidity does not imply universal rigidity? You have an example? Yeah.
Let's see an example. So I have where's the example? One second. So yeah. So I have this framework. 4. Uh, 4, 1, 2, 3. So there's four nodes, and have these vertices. So this you see edge 1, 2 is plus edge 2, 3 is equal to edge 1, 3. So this framework is not a universal rigid because you can rotate this to form, right? You can rotate it, but this is dimensional rigid in R2. No, it's actually dimensional. Yeah, it's dimensional in R2.
Okay, so dimensional rigidity doesn't imply rigidity at all, even.
Right.
Okay, so but universal rigidity does, of course. Yeah. So dimensional rigidity is simply saying that all frameworks. So neither one is a generic property, but I guess you can talk about graphs that are all generic realizations are universally rigid, and you can probably also talk about, can you do the same for dimensional rigidity? So what I'm trying to get at is this is a very highly non-generic example, right?
Yeah. For generic example, so you want a generic example?
Yeah, generic or at least general position.
General position.
That's okay. We can think about that. You can continue, and then we can maybe talk about it later. Yeah.
Yeah. Okay. Yeah. So okay. So we continue. Mm-hmm. So here the theorem about that characterize this universal rigidity, which says if a framework GP is universal rigid if and only if the two following conditions hold. So the first one is that GP is a dimensional rigid, and the second one says that GP does not admit non-trivial affine flex. So I will explain this non-trivial affine flex later. But this theorem basically says the first part says GP is not a dimensional rigid. That means that you cannot go higher. You cannot go higher. Second part basically says you cannot go lower either. So you cannot go higher, and you cannot go lower than this is universally rigid. Okay, so now I want to define what is the non-trivial affine flex. So let GP be an R-dimensional bar framework. So this framework is said to admit a non-trivial affine flex if there exists an R-dimensional bar framework GP prime, a different one GP prime, such that this GP prime is equivalent but not congruent to GP, and there is a affine transformation that transfers a pi to pi prime. Okay, so so pi is equal to a times pi plus b, where a is a R by R non-singular matrix, and b is a vector in R. So this R, of course, R is for all the vertices. R is from 1 to n. So the only if part is obvious. If GP is universally rigid, then so this theorem, I want to prove this theorem. This only part is very obvious. So if GP is universally rigid, then of course it is it's a dimensional rigid, and also it does not admit a non-trivial affine flex. So it cannot go like it cannot move inside this R along this affine plane. So it so dimensional rigid says there's no equivalent framework, but not a congruent framework of a dimensional greater or equal to R plus 1. GP does not admit a non-trivial affine flex, says there's no equivalent framework, but not a congruent framework of dimension less or equal to R. So the H part I want to say is the proof is the following. I want to sketch the proof. So the condition I condition I implies the zero is in the relative interior of the Cayley configuration spectral hadron of this framework. Because this is the condition, right? If GP is dimensional rigid, then this implies zero is in the relative interior of the Cayley configuration spectrum, where the Cayley configuration spectrum is defined as following. Basically, it's just so you can think about this as all these y, such that and this y corresponding to the non-edges. So you can actually change the modify the non-edges, right? And you still get a PSD matrix. So the Cayley configuration spectral hadron is all such y, such that S plus Yij, Mij, the Ij correspond to the non-edges. So you perturb the non-edges, length of non-edges, you still get a PSD matrix, and therefore an EDM matrix. So this condition, so this framework is dimensional rigid, implies this. Zero is the relative interior of the Cayley configuration spectral hadron, and hence the face of this Cayley configuration spectrum, which contains 0, must be equal to the spectrum hadron itself. Why? Because 0 is in the relative interior, right? So if a face consists something in the something in the relative interior of the spec hadron, then the face must be the spec hadron itself. So you can see this is true for any convex set. So you can see a simple example, right? So here is a convex set, and so I have a like this. This will be a face. This face, but this face but here all this point here, right? All this point here, all this point in the face are not in the relative interior. But if I have a point here in the relative interior, like this point, then the face of this convex set must be the it must be the whole convex set. So that's the ideal proof idea, and then the condition 2 implies that the condition 2 says that GP does not admit a non-trivial affine flex. So this says this implies the affine Hall of the face of 0 f is just 0. Hence, by combining these two things, by combining these two conditions, we obtain that f is just 0. So the Cayley configuration spec hadron of GP is 0. That means you cannot actually you cannot change the length of the 9 edges. There's the only thing is 0. So therefore, GP is a universally rigid. Okay, so this is the equivalent condition for universal rigidity. So now have a lemma which connects which uses the condition of the general position. This lemma is used for proving another theorem, but I just let's talk about this lemma. This lemma says that let GP be an r-dimensional framework with n nodes, and assume GP is in general position. Let omega be a stress matrix. So just stress, not PSD, of rank n minus r minus 1. Then the degree I must be greater or equal to r plus 1 for every node in G. So this says, there's a connection between the stress matrix and the degree of the nodes. And the assumption is that this GP is in general position. So the proof is by using the Gale matrix. So by using this, so let omega be z times phi times z transpose. So omega is a stress matrix, and we know this stress matrix has such a factorization. So if we assume on the contrary that degree I is less or equal to r, then without loss of genericity, we can assume that this vertex is the nth vertices. And then we can conclude that the first n minus r minus 1 entries of this matrix is so this is basically so that little n is the nth column of or the nth row of Z, or the nth column of Z transpose. So so that this all these the first n minus r minus 1 entries of this matrix are all 0. And because GP is in general position, then the square submatrix of Z indexed by the first n minus r minus 1 rows and columns is non-singular. And therefore you can draw a contradiction. And here, and you prove this lemma. So with this lemma, there's a theorem by Eibach and Yin. It says let GP be an r-dimensional bar framework with n nodes, and r is less or equal to n minus 2. If GP is in general position, and GP admits a stress matrix of rank n minus 1 minus r, then GP does not admit a non-trivial affine flex. Okay, so there's a I have two conditions for the universal rigidity, right? One is a dimensional rigid. The other one is it does not admit a non-trivial affine flex. And now I have there's a sufficient condition to make sure that there does not the framework does not admit non-trivial affine flex, which is very simple. First is you assume this framework is in general position, and second, it has admits a stress matrix of rank n minus 1 minus r. So there's one sufficient condition, and there's also another characterization of this non-trivial affine flex condition by Corneli, which says if GP is r-dimensional bar framework, if GP is generic, and if the degree of the vertices is greater or equal to r for each node of the graph, then GP does not admit a non-trivial affine flex. So there's another sufficient condition. Of course, there are other conditions which you can find it on the book. But this the condition about the condition that a certificate that there does not admit a non-trivial affine flex. So I have now the second part. I want to I just talk about the non-trivial affine flex part. And now I want to talk about this dimensional rigidity. First we have this theorem using the PSD stress. So which says if let GP let GP be an r-dimensional bar framework with n nodes, and r is less or equal to n minus 2. If GP admits a PSD stress matrix omega of rank n minus 1 minus r, and then GP is dimensional rigid. So this theorem is actually so remember we proved this we proved this theorem we talked about this theorem of alternative in the previous lecture. So basically says that the dimension of the stress matrix, the PSD stress is from the dual problem, right? And this G and the lifting of this bar framework is a primal. And if this GP can be lifted to full dimensional, then there does not exist a non-zero PSD. So in general, we have this the dimension of the omega if plus the dimension of the plus the r, plus r, which is the embedded dimension, the dimension of this framework. This is less or equal to n minus 1. Okay. So therefore, if yeah.
Excuse me, it's Will. What do you mean by dimension of omega? Do you mean the rank?
Oh yeah, the rank. Sorry, the rank.
Okay.
Yeah, the rank of the PSD matrix. Yeah. Thank you for correcting me. So the rank of the omega plus the dimension r is less or equal to n minus 1. So therefore, if my stress matrix, the rank is exactly n, r is less than n minus 1 minus rank of omega, so this is equal to n minus 1 minus n minus 1 minus r, which is r. That means you cannot go any higher, right? The maximum, the upper bound is r. So your framework cannot go any higher. Therefore, this framework is dimensional rigid. Now, with this theorem, we can prove the Volume Theorem, which says let GP be an r-dimensional Barre framework with n nodes, and r less or equal to n minus 2. Then, if the following two conditions holds, first, if GP admits the PSD stress matrix of rank n minus 1 minus r, which implies
So Faye, I'm a little confused by all this. So don't we already know that one of these two conditions implies the other one in the case of general position?
One of the in the case, which one?
Either two, I think 2 implies 1 maybe, or 1 implies 2, sorry. You had previously, if you scroll up, you had previously a theorem under some other condition, maybe further up. Yeah, oh yeah, here maybe. Yeah, yeah, this one.
Yeah, this one I have a general
position condition.
Yeah, but then here I don't have the general position.
So in other words, I mean, this does seem to answer the question I asked before, which would be that does all the combination of results you put here, does it imply the question I asked before, which is that if it is in general position, if a framework is in general position, then dimensional rigidity and universal rigidity are basically identical?
Yeah. Yes.
Okay.
Yeah. So yeah, so if from this theorem, right?
Yeah.
If in general position, then you have a stress matrix. Then
yeah, but you had another theorem in between about dimensional rigidity and this condition. Maybe further down.
This. No. I think this is the only theorem I think is important. Yeah. Yeah. So general position plus the stress matrix.
Yeah.
Implies the non-existence of the
affine flex, and that then gives you your
yeah, and dimensional rigid implies there is a or dimensional implies it's no actually dimensional rigid implies well, if there is a PSD matrix of rank n minus 1 minus r implies dimensional rigid, but not the other way.
Yeah, I think you had what? Yeah, what did you have just before this? Yeah, here.
Yeah, I said so. The PSD matrix rank n minus 1 minus r implies dimensional rigid, but not the other way. If GP is dimensional rigid, you may have a PSD matrix of rank n minus 1 minus r but maybe lower.
Mhm.
So it's not a this can be strictly less, right?
Mhm. Okay.
Yeah. I forgot this should be R bar. Yeah. So R bar be a and R bar be GP prime. GP be a R bar dimensional framework.
But I mean, I can't think of an example that's general position dimensionally rigid, but not universally rigid.
Yeah, you need to find an example that you find a dimensional rigid framework.
Yeah.
But does not exist PSD stress matrix of maximum rank, or rank
Yeah.
n minus 1 minus r. So
Yeah.
this is actually related to a singularity degree of the PST program, which is quite hard to imagine.
Yeah.
Yeah, this is, I know that this is hard. It's hard to imagine if such an example. Yeah, it depends on the structure of the PST and something like that. So okay, yeah. So maybe I should continue.
Yes.
Yeah. So this theorem says if GP admits the PSD stress matrix of rank n minus 1 R, then it means it implies R dimensional rigid. And then plus there's the non-existence of non-trivial affine flex. Then together they implies the universal rigid. And also this I have from using the previous theorem, you can have a theorem which uses the condition of the general position. So we said if GP be an R-dimensional bar framework with n nodes, and R is less or equal to n minus 2. If GP is in general position in RR, and the GP admits a PST matrix of rank n minus 1 minus R, and then GP is a universal rigid, which is again the general position implies the plus this PST matrix of rank n minus 1 implies the non-existence of the non-trivial flex. So you prove this theorem. So now I want to prove this theorem. So far all these conditions are just sufficient condition, right? So the sufficient condition for the universal rigidity. So it turns out that if this framework is generic, and then they are actually equivalent. So assume this the framework GP is generic, and then the following two statements two statements are equivalent. So GP is a universally rigid if and only if GP admits a PSD stress matrix omega of rank n minus 1 minus R. So first we already seen that implied 2 implies 1. This is not hard because if GP is a PST stress matrix of rank n minus R, and plus GP is generic, so generic is stronger than the general position, right? So therefore it's a GP is generic, means GP is in general position, plus its PST stress matrix, and then it implies there is no affine, no non-trivial affine flex, and also it is a dimensional rigid because the rank of the PST stress matrix. So it implies the universal rigid. So now the second part, that the one implies 2. This is the interesting part. So to prove this, we need actually a theorem, which called what's the name of the theorem? It's it's called this stress Z with stress with theorem. I don't know. So this theorem says what it says. It says that the exposed point are dense in extreme point. So what does mean? So what is the exposed point? So exposed point. So let's draw a convex set. Well, this is not a good example. So let's draw 2 parallel lines, and then have a 2 half circle. So this circle here is tangent, right? This is a 2 half circle. So I have a so here these 4 points. So these 4 points, they are actually extreme point, but not exposed point. So exposed point means there is a hyperplane, such that if y is a exposed point on the convex set C, then C intersecting a hyperplane H is exactly this y. So one example is here, right? So at this point, then I have a hyperplane, like this. So and this is my C. So the intersection is exactly this point. So what is the extreme point? Y bar is a extreme point. If any line segments, let's see, L containing if there's no line segment, there's no, if there does not exist a line segment L of this convex set C that contains a y bar. Okay, so for example, if I have this point here,
Containing y bar in the interior. Yeah.
Yeah.
So.
Yeah, you mean interior. Yeah.
Yeah, contain one as the interior. Yeah, as the interior. For example, this point, right? I have a line segment that contains this point. That's also in convex set. But here, this point, I don't have any. If I have a line segment, then either it's like this, or it's like this, or it's like that. But no matter what you do, you cannot. This line segment is nothing the convex set C. So basically, it means the exposed point exposed point are extreme point. Extreme point. But extreme point may not be exposed point. Okay, so exposed point implies extreme point, but the extreme point may not be an exposed point. So this is not true. But this theorem says this theorem says although they may not be equal, but exposed point are dense in extreme point. Then this is the proof. So how do you prove this this theorem? So the proof sketch is that so first you have a suppose we assume GP is universally rigid, and then this GP then I prove that let me see what's the I prove that it's an extreme point of the in the projection of the EDM cone project to the graph.
Maybe you have the theorem written the opposite way, maybe. Every exposed point is extreme, but every extreme point is not exposed, right? Yeah, but so the other, that should be written the other way, that every extreme points are dense in the exposed points.
So we have this point, this point, it's this point. So this point
Look
is
at
not
one of the 4 red points.
Yeah, one of the 4 point, they are actually extreme point, but not exposed point.
That's correct. Yeah, but the way you've written the theorem looks maybe should be switched.
That means extreme point are bigger. Exposed point are smaller, right? Because you can see that there's an example that these 4 points, red points are extreme point, but not exposed point. So exposed point are it's smaller set.
I see.
Point. So exposedness implies extremeness, because exposed point is like this, right? This definition of the exposedness. So so from here is this point of intersection of this common set of a higher plane.
But the point in there is not exposed, right?
Yeah.
The point in here is not exposed. Okay.
Yeah, but actually it's extreme. Yeah, extreme point. But the extreme because the definition of exposed point, because they are intersections.
All the points on interior points of the 2 circles are exposed, right?
And also extreme.
And they're also extreme, of course. Yeah. Okay.
But these 4 points are not they're not exposed.
In fact, all the points on the 2 line segments.
Yeah. Well, this point also point on are not exposed point. Because if I have a plane, then it's gonna it's gonna intersecting this whole plane, this whole segment.
That's correct, but that includes, so the non-exposed points include all the points on the 2 line segments.
Right.
Yeah.
Right. Yeah. Okay. So this and now I want to prove this. What I want to prove? Yeah.
So is it also the case that non-exposed points are dense in the extreme points?
No. Like these 4 points, right? These 4 points are they are not extreme. You have a bunch of extreme points, many, but only 4 non-exposed points. So they are certainly not dense.
Why are they only 4? That's what I can't figure out. It seems that every point on those lines, the 2 parallel lines.
Yeah, but they are not extreme point. I mean the theorem says exposed point are dense in in extreme point. So they have this. They have to be.
Oh, they're
extreme
not
point.
extreme. Why? Because you can draw a line segment directly on there, on the boundary there you're talking about.
Yeah. Yeah.
Okay. Yeah.
They're not an extreme point.
Okay.
Yeah. So so the sketch of the proof of this universal rigidity theorem use this this stressed Weiss theorem. So the idea is that you have a universally rigid framework, and then this framework well, let's say the corresponding I have the corresponding Gram matrix. I say is the R this dp is the Gram matrix or the EDM matrix of this of GP. Then X is an extreme point. Of the of this of this so you want to prove that this projection D, which is the, so let's say D is the projection of the of the Gram matrix, and the EDM project to the project to the corresponding graph. And so you want to show that this phase of D pi, so pi over kv Sn minus 1 plus is actually exposed. Why this is exposed? Because GP is generic, and therefore the projection of GP of here, right? This is equal to dp. So dp is kv x dp. Dp is the EDM of GP. So dp is certainly an extreme point. Now they are actually generic. They are generic, which means D is also generic, and D is also this D is also an extreme point. This is from the universal region. So D is a generic. D is a extreme point of this of pi. The projection of or the projection of projection of dp project to the graph G. So so the projection is because the universal rigid, the projection of this this framework, the EDM dp is an extreme point. Is actually an extreme point of the projection of the whole EDM cone. sorry, yeah. Yeah, this should be the projection of the EDM cone. So this means, yeah, this is the projection of the EDM cone on G. So D is an extreme point on this projection, and because they are generic, and the exposed point is generic, and the exposed point are dense in extreme point. That means D is also exposed point, and from exposed point, you can put in fact using the theorem from by this paper that's Henry, this coordinate shadows of the coordinate shadows of which the name paper by something I forgot, by Dimitri and Henry. So this is the main theorem of their paper by Henry Walkowitz. We said that if D is the exposed point of the projection of the EDM cone, so I have this S plus n minus 1, right? This is the PSD cone, and this is the EDM cone. And here, this is the projection of the EDM cone. So projection of the EDM cone. So if D is a exposedness of the projection of EDM cone, then if you lift it up, then there's the corresponding ground matrix is also an extreme point of the PSD cone. And then from there you can use the theorem of the alternative to argue that there exists the PSD stretch matrix of the omega of the rank n minus 1 minus r. So that's the idea. Yeah. So yeah, I think that's the talk. That's the end of the talk.